Welcome to a deep dive into a really foundational concept in computer science,
Oh,
how we fundamentally represent and manipulate graphs.
absolutely. Graphs are, well, they're everywhere, aren't they? Social networks, maps, system dependencies, you name it.
They really are, and understanding their basic building blocks is just so key to working with all that interconnected data.
Exactly. And that's our focus today.
We're using Chapter 9.2 from Hello Algo as our guide, zeroing in specifically on the basic operations you perform on graphs.
Right. Our mission, if you will, is to unpack how adding or removing points, the vertices or the connections, the edges, actually works. Like what's happening under the hood.
And crucially, why the way you choose to store that graph data makes such a massive difference in how efficiently things run.
It really does. This isn't just, theory for theory's sake.
Not at all. If you've ever wondered how your navigation app finds a route so fast, or how social media updates connections instantly, it all starts here, with these fundamental choices.
It's the bedrock for tackling more complex graph problems later on.
So let's jump right in.
Okay, so let's unpack this. The most fundamental things you do with graphs, they really boil down to interacting with those core components, the vertices and the edges.
The points and the connections.
Precisely. And as the source material really emphasizes, the efficiency, how fast these operations are, it kind of lives or dies by the representation you choose.
And Hello Algo walks us through the two main contenders, the adjacency matrix and the adjacency list.
Let's start with the adjacency matrix. That's section 9.2.1 in the source.
Okay, so imagine a big square grid, like an n by n grid, where n is just the total number of vertices in your graph.
Yeah, think of the rows and columns as labels for your vertices, from 1 to n or 0 to n1 typically.
And if there's a connection, an edge between, let's say, vertex I and vertex j, you just put a 1 in the cell where row I and column j meet.
And if there's no direct connection,
Then you put a 0. Simple as that.
and it's worth mentioning for an undirected graph where if A is connected to B, B is also connected to A, like a two-way street. The matrix is symmetric. The value at ij is the same as the value at ji.
Makes sense. Okay, now let's talk speed, performance. We often use big O notation for this, right? Like O1, ON.
Exactly. Big O notation isn't about measuring seconds. It's about understanding how the time or memory needed scales as the graph gets bigger. It describes the growth rate.
So O1 means it's constant time. Like it doesn't matter how big the graph gets, the operation takes roughly the same effort.
Precisely. Like flipping a single switch, ON means the effort grows linearly with the number of vertices in. Double the vertices, you roughly double the time.
Okay, and ON2, that sounds worse.
It is. It scales with the square of the number of vertices. So if you double n, the time or space might quadruple. That's much faster growth.
And we'll also see ON plus M, where M is the number of edges.
Right, meaning the effort depends on both the number of vertices and the number of edges. Understanding these scaling factors is absolutely crucial for picking the right tool for the job, especially with large graphs.
Got it. Okay, so with that big O context, let's look back at the adjacency matrix operations. First up, adding or removing an edge between vertex I and j.
This is where the matrix really, well, shines. It's super efficient.
How so?
To add or remove that connection, you just go directly to that specific cell at Jamadi and you flip the value. 0 to 1 to add, 1 to 0 to remove.
And for an undirected graph, you do the same for add geometry.
Exactly. And because finding a specific cell in a grid like this is a direct lookup.
It's constant time.
It's constant time, O1. Doesn't matter if you have 10 vertices or 10 million, finding and flipping that one value takes essentially the same tiny amount of time.
Okay, that's pretty impressive for edges. But what about adding a vertex?
Ah, that's a different story. If you want to add a completely new vertex, your NXN grid isn't big enough anymore.
You need an n plus 1 by n plus 1 grid.
Right, you have to physically, or conceptually at least, add a whole new row and a whole new column to your matrix.
And fill those new spots with zeros, I guess, since the new vertex isn't connected yet.
Exactly. You initialize the new row and column with zeros. Now, if your graph already had n vertices, you're essentially adding about 2n plus 1 new cells.
So the work involved depends on how many vertices were already there.
It does. It scales linearly with n. So adding a vertex takes on time, not constant anymore.
Okay, ON. Still maybe not terrible. But removing a vertex, you mentioned weaknesses.
Yeah, removing a vertex is where the adjacency matrix can get really quite slow. You have to delete the row and the column corresponding to that vertex.
Which sounds simple, but how does it actually work in memory?
Well, think about removing, say, the very first vertex, vertex 0. You delete row 0 and column 0. Now you have gaps.
Okay, so you have to shift everything.
Exactly. You typically have to shift all the rows below the deleted one up one step and all the columns to the right of the deleted one left one step to close those gaps and keep the matrix contiguous.
And shifting potentially a whole lot of elements.
In the worst case, yeah. If you remove the first vertex from an NXN matrix, you might end up shifting around N1 elements. That's roughly N2 elements.
Wow, okay, so removing a vertex becomes an ON2 operation. That's potentially very slow for big graphs.
Very slow. Remember that quadratic growth.
Definitely a major drawback. What about just setting up the graph initially?
Initializing a graph with n vertices using an adjacency matrix involves two main costs. First, you need some way to store the vertices themselves, maybe a list, which takes ON time and space.
Okay.
But then you have to create and initialize that entire NXN matrix, usually filling it with zeros. That takes ON2 time and space.
So the matrix creation dominates.
It does. Initialization is effectively ON2. You pay that cost up front.
And the code examples in Hello Algo reflect this. A list for vertices and a 2D structure for the matrix.
Yep. Typically, you'll see maybe a standard list or vector to hold the actual vertex data or values, and then a 2D list, 2D array, or vector of vectors for the matrix itself. Pretty much mirrors the concept.
Okay.
Yeah.
That gives a really clear picture of the adjacency matrix, fast edge ops, slow vertex removal, and that fixed ON2 space cost.
Exactly. Now, let's switch gears and look at the other main approach, the adjacency list. Section 9.2.2.
Right. How does this one work? It sounds like it avoids that big NXN grid.
It does. Instead of the dense matrix, think of having a main structure, maybe like a list or an array, where each position or entry corresponds to one of your vertices.
Okay.
But here's the key difference. At each position, instead of a whole row of zeros and ones for every other vertex, you just store a list containing only the vertices that this particular vertex is directly connected to.
So like vertex A's entry just points to a little list containing B and C if A is only connected to B and C.
Precisely. It's like each vertex has its own much smaller list of direct neighbors or friends.
That sounds potentially much more space efficient if there are many connections.
It absolutely is, especially for sparse graphs.
Mm.
Now, the source adds a couple of important implementation details for how this is often done in practice.
Okay.
First, instead of using a simple array where the index 0, 1, 2 represents the vertex, they often use a hash table like a dictionary in Python or a map in C++ map.
And what does the hash table map?
It maps the actual vertex object itself or some unique identifier as the key, and the value associated with that key is the list of its neighbors.
Okay, using the vertex object as the key. Why is that important? The source seemed to emphasize this.
Yes. That's a really crucial insight for efficiency, especially when deleting vertices. Think about what happens if you did just use array indices 0 to n1.
Okay.
If you deleted vertex I, what happens to all the vertices that came after it, like I plus 1, I plus 2?
Their indices would effectively shift down. I plus 1 would become the new I plus 2 the new I plus 1, and so on.
Exactly. And if you didn't update every single reference to those vertices throughout all the other neighbor lists in your entire structure,
All your connections would be broken or pointing to the wrong place.
precisely, it would be a nightmare to maintain. You'd have to potentially traverse and update everything. Very inefficient.
So using the vertex object itself as the key in a hash table avoids this.
Yes, because the identity of the vertex isn't tied to its position or index, it's tied to the object itself. When you delete a vertex, you just remove its entry from the hash table.
And when you clean up references in other lists.
You're looking for that specific vertex object to remove, not an index number that might have changed. It isolates the impact of the deletion much better.
That makes a lot of sense. A subtle but really important implementation detail. What about the neighbor lists themselves?
The source also notes they typically use dynamic arrays, like Python lists or C++ vectors, for the neighbor lists, rather than traditional linked lists, mostly for coding simplicity and sometimes better cache performance, though linked lists are the classic textbook example.
Got it. So the common setup is a hash table mapping vertex objects to dynamic lists of their neighbors. How do the basic operations perform with this structure? Let's start with adding an edge between vet1 and vet2.
Pretty efficient. First, you use the hash table to find vet1's entry. Hash table lookups are typically O1 on average.
Okay.
Then you just add vet2 to the list of neighbors stored there. Adding to the end of a dynamic array is usually O1 amortized time.
And for an undirected graph, you do the same for vet2. Add vet1 to its list.
Exactly. So adding an edge comes out as O1 on average. just as fast as the matrix for this.
What about removing an edge?
Similar idea, use the hash table to find vet1's neighbor list, average O1. Then you need to find and remove vet2 from that list, and do the reverse for vet2's list.
How fast is removing from the list? Doesn't that sometimes require shifting elements?
It can, depending on the list implementation. However, the efficiency table in the source, 9.2.3, lists removing an edge as O1 for this hash table list implementation. This might imply using a list structure where removal is fast, or perhaps it's considering the average case or amortized time. Regardless, the table claims O1.
Okay, we'll go with O1 based on the source table for this setup, adding a vertex.
Super fast here. You just create your new vertex object. Then you add a new entry to the hash table. Map the new vertex object to a new empty list of neighbors, like Agilist new vet R.
And adding to a hash table is typical.
Average O1. So adding a vertex is incredibly quick with the adjacency list. Big advantage over the matrix's ON.
Huge difference. Okay, now the big one. Removing a vertex. The matrix was ON2. How does the list fare?
Much, much better. But not quite constant time. It involves 2 steps.
Okay.
First, you remove the vertex's own entry from the main hash table. Finding and removing from a hash table is, again, average O1. That part's fast.
Okay.
But you still have that cleanup task. The vertex you just removed might have been listed as a neighbor by other vertices.
Ah, right. You have to go tell everyone else it's gone.
Exactly. You need to iterate through the neighbor list of potentially all the other vertices in the graph and remove any references to the vertex you just deleted.
How many other vertices could there be?
Up to N1 other vertices, and in the worst case, you might have to scan through their neighbor lists.
So the time depends on the number of vertices.
Yes. The source table lists removing a vertex in the hash table adjacency list implementation as ON. You have to potentially touch something related to every other vertex.
Okay, ON. Still, that's a massive improvement over the matrix's ON too.
Absolutely. Linear versus quadratic scaling makes a world of difference for large graphs.
And finally, initialization. Setting up the adjacency list graph.
If you're creating a graph with n vertices and m edges, you start by setting up the hash table, adding entries for the n vertices, each with an empty neighbor list. That's roughly ON.
Okay.
Then you process all m edges. Adding each edge is O1 on average, so processing m edges takes OM time. For an undirected graph, each edge results in 2 additions to neighbor lists.
So the total time is driven by both vertices and edges.
Right. The source summarizes the initialization time as ON plus M.
Interesting. So the setup cost reflects the actual structure, the nodes, and the connections you're adding.
Exactly, which makes intuitive sense.
Okay, so now we've seen both representations in detail. The comparison table in section 9.2.3 must really pull this all together.
It does. It's a really clear summary of the time complexities for the key operations and the space complexity. Let's recap that quickly.
Please do.
Adjacency matrix. Checking adjacency, adding edge, removing edge all O1, super fast.
All right.
Adding vertex, ONN, removing vertex, ON2, space, ON2.
Got it. And the adjacency list, using the hash table method we discussed.
Checking adjacency, adding edge, removing edge, also listed as O1 average time. So edge operations are still fast.
Okay.
Adding vertex, O1, much faster than the matrix.
Yeah, big win there.
Removing vertex, ON, way better than the matrix's ON2.
Also a big win. And space.
Space is ON plus M.
Okay.
Depends on both vertices and edges.
So the differences really pop out when you look at vertex operations and memory usage.
Absolutely. That's where the trade-offs lie.
The matrix uses that guaranteed, potentially large ON2 space, regardless of how many edges there actually are.
Right. It reserves space for every possible connection.
Like you said, seats reserved for friendships that don't exist.
Exactly. Whereas the adjacency list only stores the connections that do exist. Its ON plus M space usage is much better for sparse graphs,
Define sparse again.
where the number of edges, M, is much, much smaller than the maximum possible number of edges, which is proportional to N2. Think of a social network most people aren't directly connected to most other people. M is way less than N2.
So for sparse graphs, the adjacency list saves a ton of memory.
A huge amount, potentially. For dense graphs, where M gets closer to N2, like a graph where almost everyone is connected, the space difference between the 2 representations becomes less significant.
Okay, so space is a big factor. What about time again?
The matrix wins slightly on simplicity for edge check SADS removes being strictly O1, while the list is O1 on average due to the hash table. But the list absolutely crushes the matrix on adding vertices, O1 versus ON, and especially removing vertices, O1 versus ON2.
So what's the big takeaway? How do you choose?
The source puts it nicely. The adjacency matrix exemplifies space for time. It uses potentially lots of space, O and 2, to get guaranteed constant time for those edge operations.
And the adjacency list.
It's often seen as time for space, although maybe that's not quite fair with the hash table version. It uses much less space, O(n plus m, for sparse graphs, and actually achieves better time complexity for vertex operations while keeping edge operations competitively fast on average.
So the choice really hinges on what your graph looks like and what you'll be doing with it most often.
Exactly. If you have a very large but sparse graph and you're adding or removing vertices frequently, like users joining, leaving a network, the adjacency list is almost certainly the way to go. The memory savings and faster vertex ops are key.
But if you have a smaller, maybe denser graph, and you're mostly just checking if edges exist or flipping edges on and off, and vertex changes are rare.
Then the adjacency matrix, with its simplicity and guaranteed O1 edge ops, might be perfectly fine, or even slightly preferred perhaps for its predictability, maybe even cache behavior in some specific cases, although that's getting deeper.
It's a classic trade-off, isn't it? Understanding these two fundamental structures and their performance characteristics is just so essential for anything else you want to do with graphs. It really helps you remember why certain choices are made later on.
It really does. It provides that crucial foundation, that deep understanding of the mechanics.
So we've really dug into the two core ways to represent graphs, the adjacency matrix and the adjacency list. We've broken down how those basic operations, adding, removing, checking vertices and edges, play out differently for each one.
And hopefully highlighted those critical trade-offs in time complexity, like O1 versus ON versus ON2, and space complexity, that big difference between ON2 and ON plus M. Understanding that is just, well, fundamental.
Absolutely. This knowledge really sets the stage for everything else, finding shortest paths, looking for communities, analyzing flows. It all builds on this.
It's definitely the starting point for a lifetime of understanding graphs.
Okay, before we wrap up, here's a final provocative thought for you, the listener, to chew on. Think about a real-world network you interact with regularly. Maybe it's your city's road network. Maybe it's the web of links between websites. Or connections on a professional network like LinkedIn.
Lots of examples out there.
Considering the likely characteristics, is it sparse or dense? How often are nodes like roads, websites, people added or removed? How often do you need to check direct connections versus find all neighbors?
Which representation, adjacency matrix or adjacency list do you think might be powering it behind the scenes? And more importantly, why would that choice make sense given the trade-offs we've discussed?
Something to ponder about the hidden structures shaping our digital world.
Definitely food for thought.
We'll catch you on the next deep dive.